Astronomy Cast, episode 262 for Monday, April 23rd, 2012. Solar Sails. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hi, Pamela. How you doing?
I'm doing great. How are you doing, Fraser?
Doing really well. Now, I think we need to give people another reminder that the world is not going to end this year and will be there to celebrate its continued existence.
Yes. So we are going to be going on The World Is Not Ending cruise, and you are all invited to join us. It's a cruise that goes out of Miami, leaving December 16th, and travels to a bunch of awesome places, to a couple of awesome countries. And we're actually going to spend the day the world is supposed to end at Mayan ruins. And I love archaeology. So
Yeah.
we're doing this, and we're inviting you to do this with us. And if you go to astrosphere.org, which is the nonprofit that co-sponsors this particular podcast, there's all the information that you need to sign up. And basically, we're working with a travel agent. Her name's Zelda, and when you call up Zelda, just tell her Astronomy Cast sent you, and she'll get you all hooked up with cruise tickets and an awesome chance to be in on a bunch of private recordings, a bunch of special events, and getting to see me look foolish trying to climb around archaeological sites.
And the actual cruise itself, there's a ton of really interesting stuff on it.
Yeah.
David Brin is going to be there, a bunch of astronauts, other astronomers, so it's going to be a very space-focused cruise. And so if that's your thing, we'd love to have you guys join us. So like I said, go to astrosphere.org. There's a link there, and then make sure that you say that Astronomy Cast sent you so that we know that we will know how many people are going to be coming to sort of participate in the things that we're trying to do.
Yeah, and how awesome is it that our travel agent's name is Zelda? That's just part of my favorite.
The world. It has been prophesied that we will be going to the Mayan ruins by Zelda. All right. Well, let's get on with today's show. So now, wouldn't it be cool to explore the cosmos powered only by sunlight caught by your shimmering solar sail? It sounds like science fiction, but it's serious science. A test sail has even been sent into orbit. It might even be a way to travel from star to star in the far future. Solar sails. I love solar sails. I'm a sailor, so I think it's just a natural fit to turn it into to do solar sailing as well. But I do think that the actual realities of it are going to be a little different for people, and I know there's a few surprising things that I remember. Even a few years ago, you explained a part to me of solar sailing that just completely changed my whole perspective on it. So I will definitely be digging that up from you this episode. So then, what is the sort of the physics going on? Why does a solar sail even seem like a viable way of moving through space?
Well, this all goes physically back to that whole E=mc² part of reality, where light is able to impart momentum. So if you shoot someone with a laser beam, you're actually pushing on them. And when we look at stars, we're seeing objects that are very carefully balanced between the force of light pushing out, light pressure, and the force of gravity pushing in. And we just don't think about this in our day-to-day life, but when it gets to be outer space, it was noted as early as Kepler that there seems to be this force that pushes comet tails so that they're always pointed away from the sun. And so even before we realized that light was able to exert a pressure, Kepler was thinking this might be a way to actually sail through the heavens. If the solar wind can push the comet tails in a constant direction away from the sun, maybe it can also push human beings in great sailing craft away from the sun as well.
Now, but those are kind of different, right? I mean, the solar wind and the light pressure from the sun are two different creatures.
Right. So the light pressure from the sun is literally the pressure of light, and the solar wind includes a lot of particles, a lot of other stuff that's getting blasted off the surface of the sun. So it does get a little complicated. But it's really the radiation pressure here that's exerting the majority of the force. But Kepler, he didn't know any of this stuff. To him, it was all wind.
It's all wind, yeah.
It's all wind. And what's kind of awesome is he actually wrote a letter to Galileo in 1610, and I just love this quote. He wrote, provide ships or sails adapted to the heavenly breezes, and there will be some who will brave even that void. And it's just this great romantic idea of this great Argonaut just sailing between the planets.
Now, when we take, I know, like for a lot of it, the analogy holds. I mean, with sailing here on Earth, you've got the wind is pushing in a constant direction, and when you're going with the wind, it's really the wind is pushing you in the same direction that you're going. And that analogy really holds out in space as well, that if you set up some kind of sail, you're going to get pushed in the direction that the light pressure is going, and you're going to be pushed, accelerated away from the sun.
Yeah.
But here on Earth, when you want to sail into the wind, there's a sort of a different technique that you have to use, where the boat has a keel, will have some kind of dagger board that sort of pushes against the water and then actually lets you move upwind. But it's completely possible to move upwind in space as well. It's all more about orbital mechanics than it is about actually using some kind of keel.
So where in space, you have no drag, you have almost no friction unless you're close to the atmosphere of a planet. So that normal idea of dropping your keel, creating the friction, using the water to help define your direction. In space, you just have to basically say, okay, there's gravity pulling me over there. Let me lessen the amount of force that's pushing on my sail by rotating the sail. You have to try and balance the forces to figure out where you're going. But if you don't have a force where you want to go, you can't go that direction. So it's simply a matter of letting go of the wind and falling into the sun, or rotating your sail to catch the full light and getting pushed out of the sun.
Right, so let's talk a bit about that, about how you would move through the solar system. So let's say that we launch a solar sail from Earth, put it into orbit, and now it's in orbit around the Earth, or perhaps in orbit around the sun, in the same kind of roughly orbit that the Earth is going. So how would we move? Let's say we wanted to visit Jupiter. What would we do with our solar sail?
We would, first of all, it would be a very, very, very slow process. That's the first thing everyone needs to understand. This is a slow process. You're looking at maybe a Newton of force, and a Newton is enough to lift 1 kilogram, 1 meter, and yeah, it's not a lot of force. So you're looking with your very small amount of force. You're going to pivot your sail to catch the sunlight, and you're going to very slowly move into a higher and higher orbit. So you're probably going to do this in a systematic way, such that you always apply the force at the same point in your rotation around the Earth, so that you can constantly get higher and higher and higher in a systematic way, just like you might always fire your rockets when you're at the same point to get your orbit larger and larger. Once you finally escape the Earth's orbit, you want to escape such that you're still arcing toward where the object you're trying to get to will be when you get near it, so that you can gravitationally, hopefully, get captured from it. Along the way, you may get lucky and have orbits aligned such that you can use the gravitational assist of objects between here and there. But in general, you're going to, the entire time, just tack your sails to increase or decrease the force that you're getting, such that you're accelerating away from the sun in a way that adjusts your orbit as needed as you move from a planetary orbit to a solar orbit.
And if you looked at the orbit, I guess the path that the solar sail had taken to make this journey, you would see this ever-expanding spiral, because you would be, and I think a great analogy of that is there was the mission, there's the Smart 1 mission that went to the moon, and they used an ion engine. And what they did was they were orbiting the Earth, and they went around and around and around, and just in wider and wider orbits until they got captured into the lunar orbit, and then they came the other way and went in and in and in until they were actually orbiting the moon instead of the Earth. And it's this same situation. If you use a solar sail, you're going to be using that power, that acceleration from the sun, to just increase the size of your orbit away from the sun, to put you into higher and higher solar orbits until, I guess, your orbit overlaps Jupiter's orbit, and then you're going to try and get yourself captured by Jupiter.
Now we are giving one bad impression with our use of the word "your" in all of this. This isn't going to be human beings. Solar sails are a wussy way to accelerate something.
Unless you use lasers.
Then it's a very energy-intensive way of traveling and not practical. So we're really looking here at nanosats, at CanSats, at spacecraft that make my iPod look heavy. We're not going to be building things that move human beings and their orbital habitats and their life support systems and everything else, simply because it's just not a practical technology for that.
Yeah, well, this is the part where I'm going to stick my fingers in my ear and say, la, 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 not listening. So you can say that if you want and dream about nanosatellites moving to higher orbits, but the reality I know is that we're going to have crude sailing ships plying the spaceways. So, but I think what was really interesting, what's really important about this, I want to really get this into people's brains about this spiraling nature of the orbits, because that's the key on how we also descend in the solar system as well. That's how we go from, say, the Earth to Venus. You know,
Right.
you may ask yourself, if the sun is pushing outward this whole time, how do we go from the Earth down to Venus?
Well, so in that case, you simply look to apply the force in a direction that hopefully slows you down somewhat. It's all a matter of angling things. So if you're traveling in a circle around, let's make my microphone the sun. If you're traveling in a circle, there's different ways to expand your orbit so that you make it different shapes. And it's tricky, because to get a smaller orbit, you do need to slow down, which means you essentially need to figure out how to accelerate in the opposite direction that you're traveling in. Now, the solar sail can really only push you away from the sun, so it's a matter of figuring out how to do that in a way that adjusts your orbit such that while you're going further from the sun on one side of the orbit, you're able to change the angle enough so that hopefully you can get closer to the sun on the other orbit. And it's non-trivial. It's you're basically looking for something that will gravitationally slow you down, because you're not really going to use the solar sail to slow you down. You're going to look for it to adjust your orbit so that gravity can slow you down somewhere.
Right. And you know, the analogy that I always use is that you put your arm out the window of the car while you're driving.
Yeah.
You put your hand flat out the window, and then if you tilt your hand up, then you're going to have this lift on your hand, and it's going to want to push you up above. But if you tilt your hand down, now you've got a sort of a pressure that's pushing your hand down. And in the case of with the solar sails, right, we're tilting the sail so that pressure from the sun is going to be decreasing at the speed of your orbit and drop you into lower and lower orbits, right?
This is where the whole analogy with real sails actually completely breaks down.
No, I know.
And the hard part is with a sail, one of the forces that you're dealing with is you have lift. So you have a lifting body, and the physics of lifting bodies is extraordinarily complicated. The truth is, wings are not as easily understood as most aerodynamic books will try and make them understood. But solar sails aren't a lifting body. It's simply a force pushing away from the sun. And you're not going to be able to get any of this getting sucked forward or backwards lifting effect that you get with wind. It's simply a force that always pushes in a straight line away from the sun. And so that's where it suddenly becomes a getting near the sun means you have to find something else to gravitationally slow you down, and you just let go and fall.
Right, exactly. So let the gravity of the sun pull you back in.
Yeah.
Using other bodies. So then what kind of material would make sense for a solar sail?
This is something that folks have actually been actively struggling with. Many different teams are trying to figure out how to build solar sails. Problems that they're running into is things like struts that are capable of supporting all of the force on a very thin material without tearing or breaking, building things as light as possible. But at the end of the day, what we're looking at is plastic films, things like mylars that balloons get made out of, and very thin plastics to build the struts. These things basically look like giant kites, giant pinwheels, and it's amazing how big they have to be and how thin they have to be. So we're looking at things that are measured in nanometers. So maybe as thick as 100 nanometers, that's smaller than a hair. And not only are they extraordinarily thin, but then you have to figure out how to pack them up and deploy them without them getting tangled, without them tearing. And so you're building something foldable, fragile, capable of sustaining all of the force against it without tearing, and capable of unfolding in a graceful way while minimizing weight. And it suddenly becomes just this huge furry deal that we don't always succeed at.
I know that origami folders have been called in to this challenge. I know there was actually a folding telescope that was designed with the help of some origami, but I'm sure the same thing's going to happen with creating these solar sails. How do you fold up something that's a kilometer across into a small package so you can even launch it into space? And then how can you have it unfold so that all the struts work properly? Because, I mean, we've even had problems with solar panels coming out.
Right.
Where like, oh, the solar or the remember the Galileo spacecraft with its fold-out antenna. That sounded like a good idea at the time, but it didn't work.
And so here we are trying to figure out how to build things that, well, are 20 meters. That's 70-ish, 65-ish feet in width and height. 20 meters across that fold up into little tiny spaces and have struts that safely hold them open and are carrying little tiny CanSats on them. And so suddenly it just gets extremely complicated to do this in a safe way. We've used aluminums, we've used plastics, we've used polyamide, which is just a fun word. And they're getting to the point that some of them are deploying, some of them are not, and so far we haven't been able to successfully build one that both deployed and was successful in pushing the spacecraft somewhere.
This might be one of the challenges that will be met only by some kind of space-based manufacturing, where you've got these asteroids that we're tearing apart by planetary resources and turning them into solar sails to move material around the solar system.
Actually, you're not going to make plastic out of asteroids, so that probably won't happen.
That's right. You need dinosaurs for that.
You need dead dinosaurs to make solar sails.
Right.
It's true. It's sad, but true. Solar sails are made of dead dinosaurs converted to plastics. So I think it's something that we're actually going to figure out soon, but it's one of those things that it hasn't been a primary problem that either NASA or ESA or any other organization has been dropping a lot of resources into. We've seen the Japanese try at it, we've seen the Russians try at it, we've seen the Europeans try at it, and right now one of the primary efforts is actually coming from the Planetary Society here in the United States, where they're actively working on Light Sail 1, where they're working to try and define what is the most effective way to build this, what is the most effective way to deploy this, and it's something that they will be doing in the near future. So it's just interesting to see that not only do we have commercial space agencies that are actively working to try and build things like Dragon, but we also have nonprofits working to try and solve some real issues in space exploration and build solar sails and CanSats.
Yeah, and a quick shout out to the Planetary Society and our good friend Emily Lakdawalla and Bill Nye the Science Guy. Right. But if if this kind of technology is interesting to you, you should absolutely join the Planetary Society, give them a donation, help them out with their plans, because they've been actually creating solar sails and actively discovering how hard this is. But I mean, they've actually launched a sail.
Well, they have, and it wasn't a complete success, but it's progress. Mm-hmm. And what's kind of awesome about this is it's a fairly low-cost technology. It's a annoyingly difficult technology to work with, but it's a low-cost technology. And as the price of sounding rockets drops, as the price of launches of CanSats drop, it starts to become the type of project that a university engineering class has the potential to work on. This is within reach of working with folks like Kentucky Space, which is another organization to give a shout out to. So in the near future, this is conceivably a problem that's going to get solved by a bunch of aerospace engineering graduate students or even undergrads working hard with a bunch of mylar and aluminum.
So let's sort of imagine the near future or the middle future, you know, maybe 10, 20, 30 years down the road when planetary societies tests have yielded some success and Planetary Resources is incorporating, you know, they're launching plastic to be able to build their solar sails. You know, how would a solar sail propulsion system fit into the sort of the various propulsion systems that people will be using to get around the solar system? When would they choose it?
Well, it's definitely something that's an inner solar system technology. And it's the type of thing where you can imagine you fire something off to one of the inner planets and you want to send something back, you get it back to orbit and then attach it to a solar sail and use the solar sail to get it back to Earth. So this is a way of getting a free return trip that just requires a great deal of origami. And so these are the nice types of easy projects. Send a couple rocks back. They have to be small rocks. Can't carry much mass. But it's a way to get things back to Earth from the inner solar system. It's also a way to get things perhaps out to the outer solar system at low cost. You can almost imagine a future where if you want to send a gift to your relatives on Mars and it weighs a small enough amount, you send it via solar sail post.
How long would that take? Years?
A long time.
Yeah.
You have to think ahead. But it's not fast. It's not good at sending large amounts of mass, but it's that slow and steady gets the job done at a low cost.
Could you see it as being used as a transfer system between Earth and the Moon? I mean, like sending supplies. You can imagine solar sails making some kind of complicated orbital mechanics.
To a solar sail, not effective for carrying supplies.
Not effective for carrying supplies. I think that's just a failure of your imagination.
I think it's a failure of wanting to build something that big. I mean, it's a reality of just how much light we're getting from the sun. At a certain point, you can't turn up the sun. And so when the total force exerted on a normal solar sail is enough to lift, this weighs less than, so big solar sail, you're looking at being able to move a 1 kilogram object ineffectively. And it's simply the limitations of how much pressure we're going to get. The energy that we get, it's proportional to the energy of the photon divided by the speed of light. That gives you the momentum. That's the change in energy that you get. We're not going to be able to change the energy of light coming off the sun. We're not going to be able to change the number of photons coming off the sun. Between here and the moon, we're a high gravity environment. Low Earth orbit, you're dealing with the drag of the Earth's atmosphere. One of the numbers that I've looked up, its estimates are you're looking at 4.57 times 10 to the minus 6 newtons per square meter of a solar sail.
That's small.
That's very small. So this is why I'm going to stress over and over, not how you're sending supplies.
You are such a buzzkill.
There's ion drives.
Fine, okay, all right.
So, if you want slow and steady.
So the solution to solve this problem is lasers. Big lasers. Now, I know that's energy intensive, but the point being you can be on Earth and you can shoot a laser into space. Yes. And that's a way to get your power from Earth to space and apply a force. Now, can you just shoot a laser at a solar sail and impart force on it?
Yes. That's one of the nice things about this.
Well, then there's your problem solved right there. But
Now,
obviously, what are the technical constraints of such a
well, so the
energy?
problem that you're going to have with that is laser beams get scattered by the atmosphere. They broaden as they go. When we shoot lasers off the moon, we're looking at only getting back, maybe on a really good firing, a dozen photons from that laser beam.
And it's a really powerful laser.
Yeah, so we're not looking at this being any more effective, really. Now, in the future, where you can sort of imagine petawatt lasers, lasers that in a single burst use the same amount of electricity as New York City, we're looking at destroying the Earth's resources in order to be able to push a small object through space.
I can totally imagine that future.
I love how you're so willing to sacrifice the Earth to use solar sails.
Whatever it takes. Whatever it takes. We gotta tear apart huge chunks of the Earth and turn them into lasers so we can fire them our solar sails, so we can have our 2080 solar system cup. I'm all for it.
Student projects. This is excellent technology for future student projects, launching CanSats that are capable of interplanetary flight.
Yeah. Now, what about the potential for using it as another, like a long-term technology to get from star to star? I mean, again, if time is no concern.
Right. So this is a way to get you out of our solar system. To give you a realistic idea of the effects of solar pressure, a spacecraft going from Earth to Mars is going to get displaced 10,000 kilometers by the pressure from the sun. Now, if you just let that go, if you put that giant sail out, this is going to add up over time. It's going to keep pushing you out. Now, the issue is, at a certain point, you're going to get far enough from the sun and everything else that you're no longer experiencing any real noticeable external force due to radiation pressure, or the sum of the forces is going to basically add up to zero.
But you got momentum from your.
But you have momentum.
Release.
This is what's carrying the Voyager spacecrafts out. So you use this to get very, 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 very slowly out of the solar system. But again, ion drives, much more effective.
Yeah, but you got to carry your fuel, right? And so then you aim at a star, and then you
brake.
But
ions don't require all of that much.
And then you brake using the light pressure from the star that you're going towards. Right? You've got a way to accelerate yourself and a way to brake, and you didn't have to carry any fuel, and it is awesome.
And very slow.
Man, you just are not... Where's your imagination today, Pamela? Come on.
I want effective space travel.
All right. Effective space travel. That's SpaceX. Hop in your chemical rocket. Away you go. Yeah. So that's cool. So where do you think this is going to happen? So do you see this being the future of these nano satellites? Can you imagine people deploying a lot of really small satellites that have like single purpose that might cost?
I think this is going to be a really neat low-cost way to do simple exploration projects. It's going to be the way that we get small cameras doing interesting things. It's going to be the way we collect dust. It's going to be the way lots of little things happen that you don't always need to take the kitchen sink into outer space with you. And this is a great way to do those little tiny single-purpose, low-cost spacecrafts once we figure out the technology. It's a technology that is still unproven. Folding those suckers up is turning out to be way more complicated than anyone imagined. But once we figure out how to fold them, once we figure out how to deploy them, once we figure out how high up they need to be before you deploy them so that the Earth's atmosphere isn't an issue, I then think that we're going to have a whole new, interesting way to do low-cost space-based science.
All right. That was kind of inspiring. I'll go with you there. Well, that was great, Pamela. Well, thank you very much, and we will see you in the 2080 Solar System Cup.
Sounds great.
All right. See you next week.
Yep. I don't know why I act like we're ending this forever when all we're doing is stopping the recording and saving it.
Yeah.
Okay, so once we're done...
This will happen again, Pamela. Don't worry. I know you really enjoy recording episodes of Astronomy Cast, but we will be doing this again.
No.
So that was 262.
Okay. Switching over to find what window. There it is.
I've saved.
That is a good thing.
And now I'm doing it.
Phoenix Torres writes, don't observe, you might change the state of the hangout. I love quantum mechanics jokes. So Shiraz Sadiqwa, I'm so sorry, I know I pronounced that, said, can you guys share an astronomer circle for me to add? Yes, Fraser has an amazing one that I will let him talk about.
Sure, I have 3 circles, so you can choose whichever one you want. I have my Super Science Circle, which is active people who talk about science on Google+. I have a space and astronomy one, which is not necessarily active, but everybody in it is space in some way. And then I've also got an astrophotographer one that has about 15 people that just deliver pictures of astrophotography, although it's kind of melded into the space one. So I will share my space one. If you look back through my past, you do a search on it, you can probably find it, but I will share it at some point, or I'll even share it right at you. So, but yeah, that's something that I do.
So there's someone who asked a question, sorry, I flipped between windows, about whether or not the material used for the James Webb Space Telescope sun shield would be effective for a solar sail. And I think the material's too thick. I'm looking to check right now, but I think it's just a little bit too heavy and thick for that.
I wonder what impact that, I'm sure they've had to do the math. I mean, that sun shield is going to be acting like a solar sail, and it's going to be exerting a constant pressure on the James Webb in directions they probably don't want it to be going, and they're going to have to take that into effect. There was actually some research that was done in just a couple of days ago on the Karski Effect, which is this technology that pushes the asteroids around in the solar system. And they actually think that actually plays a pretty big role in contributing to nurture.
Okay, he is coming back in.
Hey, that worked.
Yay.
Yay, and it's still in the same location? Wow. A graceful recovery from a crash. That's amazing.
They're getting better with this technology.
Yeah, absolutely. Yeah. Don't count it out. It is not a ghost town. I don't know, where did I get to on my rant? Did you hear me talking about the Karski Effect?
Yes, yes. And apparently when you're not here, it goes black. So I'm hoping that someone will tell us that the recording is well recording.
Oh, I see what you're saying. So can anyone still see us, I guess, in the chat?
Yeah. Okay, so I just had someone confirm no, we seem to be down.
Maybe it's not live. Let me just check. At least we got to the end of the recording the episode.
Yeah. So it says you are blank, just the Google Hangouts logo.
No.
Do we want to restart the Hangout?
See, it says 46 viewers, 47 viewers.
That's so weird. I'm asking.
No, it says we're live. You just need to restart your stream from the. Okay, so people people can see us.
Okay.
Yeah. So, I guess the people who they have to reload the page if they want to see it.
Okay, I'm leaving that in the comments.
Yeah. So, all right. So, mentioning the Karski effect. This is this pressure, the light pressure from the sun hitting asteroids and heating them unevenly in ways that they'll then, both be pushed by the sun. You can imagine an asteroid. In one way, it's broadside to the sun, and then another time it's more to the end of the sun, and so you're going to get this situation, and then it's going to be radiating heat gathered by the sun in weird directions as well. And over the course of millions and billions of years, it causes these asteroids to move in really weird ways, almost like they're being thrusted around by the interaction with the sun. And this is one of the causes of near, possibly the causes of some near-Earth asteroids, the fact that why we're still at risk to being hit by asteroids. And so this effect plays a role in many spacecraft, in observatories, and so I'm sure with the James Webb, they're going to have this constant light pressure hitting this gigantic solar panel, sunshade, all at the same time, and it's a problem.
And it is something that they've had to do calculations about. I've heard some folks from James Webb actually being very sad about having to sort all of this stuff out, because it is a complicating factor, but it is something that the best minds in our field when it comes to spacecraft design are actively working to make sure that that's one spacecraft that works well.
Yeah.
We all will hold our breaths between launch and when it unfolds.
Yeah.
There will be many blue-faced astronomers.
All our hopes and dreams rely on that spacecraft, unfortunately. Did you hear that that SpaceX signed with Intelsat for the Falcon Heavy?
No, that's awesome.
Yeah, so it's going to be capable of twice the launch mass of any other spacecraft out there.
Awesome.
So they are about to wrap up the entire launch market.
My favorite quote from the SpaceX launch of the Dragon capsule was the astronaut saying that the inside of it smelled like a new car. Because the ISS is like the stinkiest
That's what I hear.
It knows that we're done recording Astronomy Cast. And
you know what?
we're simply having fun.
I'm not going to touch my computer.
And it's punishing us.
I could be like running out of memory or something. I'm just not going to, because I'm loading up Windows and looking at things, and I wonder if that's happening. Peter Baxter wonders, in the future, could neutrino sails be possible? If you made sails out of a super-duper dense material, then you could have an unlimited energy supply, though as neutrinos come from everywhere, steering could be difficult. So now obviously there's some science problems or some materials problems there, but theoretically, could you get energy from neutrinos streaming from the sun? Don't tell me it's hard. Tell me if it's possible. Do the laws of physics prevent it?
Pretty much.
They do not.
Excuse me, neutrinos don't really interact with things.
But you said don't really.
So if the probability of interaction is so small that you can't feasibly build a material...
You said feasibly and material.
This falls into the same category as DNA belongs to one person, even though there's a statistical possibility that two people have the same DNA.
Okay, so when a neutrino goes through a light year's worth of solid lead,
yes,
and it finally interacts with some of that lead,
yes,
does it impart energy to the lead?
Yes, but the
Perfect.
sum of
So
all the
will
neutrinos
the lead
coming are going to go to zero because all of space is permeated with neutrinos.
So will the lead then get momentum and start moving away from the sun?
If the sum of all of the neutrino interactions is zero, no.
Is there more neutrinos passing through any spot in in any one spot in the universe? Or like if I was standing right beside the sun, would I be getting more neutrinos from there than from all of the neutrinos streaming from the rest of the universe?
I have no idea.
I'm going to chalk this up to probably. Yes, we can build.
So you like to say that we can do things that don't make any sense. So the problem is that
we've talked about
neutrinos
crashing
don't
black holes
interact.
together. We've crashed matter and antimatter black holes together.
So the problem is neutrinos don't really interact.
Right.
And if you have a light year's worth of lead,
Mm-hmm.
the energy from one neutrino is not going to do anything useful.
Right. So we create a solar sail made of black hole, and then every neutrino that hits it imparts a momentum to it, right?
Yeah, that doesn't work in so many different ways.
All right. But I mean, we've talked about neutrinos being a possible form of communication, that you could stream neutrinos to somebody and you could, you send them in bursts and you could send Morse code to another. Yes, most of them are going to slip past, but you might be able to get a certain number of neutrinos. So theoretically, it's possible. Anyway, super unfeasible, I guess, is the point.
Yeah.
That if you could pick anything else streaming from the sun and use that instead.
Yes, light is much better.
Light is much better.
It does interact.
And don't forget about light. But as Peter said, that you've got these neutrinos coming from all directions, and so you get far enough away, and you would then sort of lose that.
And it's also a matter of these suckers are changing identity as they go, and the different types interact with materials in different ways. And this is where, when you're near the sun, yes, there are way more neutrinos when you're near the sun, but then the quandary I'm having is, are the neutrinos you get when you're closest to the sun useful or not? Or is it the background neutrinos that are the useful ones? Or I just don't know which are the ones that are going to be the most useful for getting something that readily interacts. And they don't generally. It's just easier to use light. Use light.
Okay. So Josh Andrews notes, when you said you can't change the energy coming from the sun, he said you've obviously never seen sunshine. Clearly we only need some thermonuclear bombs. So a couple of thermonuclear bombs and you can change the energy coming from the sun.
Yeah, no, the sun won't care. The sun could eat a planet and it would still not care.
It's still not. The sun could eat another sun.
Well, then it would care.
A little bit.
A lot.
Not
it would
5
change what
suns.
type of star it is.
Not 5 suns. 2 suns. Anyway. So Josh Andrews asks, would it be feasible to use solar sails to divert an Earth-bound asteroid?
Yes. Yeah.
Yes.
This is. Yeah. Yeah. Don't need a whole lot of stuff to do that. It's still much easier to put a refrigerator in front of the asteroid and let the refrigerator's gravity pull it sideways.
Right. And if anyone has no idea what you just said, that's this concept of a tractor beam, right? So you take like an ion-powered spacecraft that's got a chunk of mass, and you hold the mass like a magnet right next to the asteroid that you're trying to divert. And then the asteroid tries to move towards the chunk of mass, and then you use your spacecraft to constantly tug in the opposite direction. And what you'll get this slow, steady gravitational acceleration applied to the asteroid, so it's going to move into some new orbit that you need.
If you want to move something heavy, don't use the solar sail.
But the other idea is that you paint your asteroids.
Yeah.
And so then by painting them, you take advantage of this effect that I mentioned, this Karski Effect. And so if you were careful to slow down the rotation of the asteroid to the point that only one side was facing the sun, and then you painted it, then you would get this light pressure pushing on the asteroid that would then move it into a different orbit. And if you had enough time, if you have enough time, all these asteroid shifting ideas come into play. There's lots of them. It's when you don't have a lot of time, things come straight at you. When you start everything looks like a nail to your nuclear weapon. And
this is why we're trying to find as many of the near-Earth objects as possible well ahead of time, and surveys like the Catalina Sky Survey, the Large Synoptic Sky Survey that's in the process of being built, all these different robotic systems, while it sometimes feels like the robots are taking over astronomy, they're also helping to protect the human race by finding all the things that might plow violently into the Earth and destroy cities, continents, the whole human race.
In fact, there was just a study done that the current number is about 4,300 asteroids,
Yeah.
but of which only about 10% have actually been found and sort of they have their trajectories appropriately plotted out. So there's still
Right.
90% of them are unknown. We just know how many there are. As we described in Universe Today, we said 4,300 asteroids want to kill you.
Yes, and that would be true.
Okay, so Thomas, that's a good question. Thomas Traneker asks about ion drives. Can you scale up those drives to get more acceleration in the drive, or is it just a power issue? And that's something I've always wondered, which is that we always talk about these ion drives having, a paperweight's worth of acceleration
Right.
to the spacecraft. But could you get more ions accelerated at the back of the spacecraft and impart a bigger thrust?
Yeah, it's simply a matter of trying to build the engines effectively enough. So this is a somewhat scalable technology. We're just still working on scaling it successfully.
So right now the problem is that you need like a magnetic chamber, and you need a way to emit the xenon ions, and you need a way to channel them and shoot them out your thruster port.
And all of that requires electricity.
So
and it's a matter of making all of this much more effective so that the energy in, energy out, all of it balances out and you can keep going long enough.
Right, but you've got a situation where, this is where the cubed law comes into play of magnetic fields, that you've got to sort of channel it with a magnetic field, and as you try to scale this up, then you need more electricity to actually target them out the magnetic field. And so there's probably only so big you could make one of these thrusters,
right.
and only so many ions you can be getting out at the same time before.
But we haven't maximized it yet.
No, but then you might need to build a second thruster and then a third thruster, and where you find this perfect happy place. But
right.
But you're saying theoretically you could build a huge bank of 1,000 thrusters powered by some kind of nuclear reactor.
They're always going to be powered by nuclear reactors.
Right, and they're all powered by solar power right now. No one's built a nuclear-powered.
That's true, but big ones, you're looking at nuclear power.
Well, that's it, yeah. So if you have a huge nuclear engine powering the electricity that's firing the ions out the back, and you build a big bank of them, you could eventually achieve a significant amount of thrust.
And doesn't New Horizons have, and I'm Googling here, but I thought New Horizons actually had a nuclear, because it's going far too far out.
Well, it's got one for its own energy generation, right? It's got one of those, was it RTG?
Right. So
Yeah.
It's a radiothermal.
Yeah.
So no, it's not solar panels.
No, it's using it, but it's not using it for its. I don't think it's using it for its engine. It used a traditional Mongol rocket and then used gravity assist from Jupiter to get to speed.
That's right. It's Dawn that's an ion drive.
Yes, but it's a solar-powered one.
My missions.
Yeah.
Okay.
So no nuclear-powered ion engine system has been deployed yet, but this was the thinking that was going to go into this mission that got scrapped, that was going to be exploring the icy moons of Jupiter, because you would end up with a spacecraft that had the ability to get itself into orbit and then back out of all of the moons of Jupiter. And that required a lot of power. But an ion engine is the perfect thing to do it. You just need this great big nuclear engine to put out the electricity required to be able to get that thrust going. So.
And one of the problems that we have here in the States right now is we don't have any nuclear engines left. The materials needed to make the radiothermal generators were out. And so we need to get Congress and the Department of Energy to fund the creation of more of these radioactive materials. But that's not happening right now, so it keeps it interesting.
Yeah. But I think there's going to be a big demand for those, and so I'm sure more of them will get built.
Yeah.
And if not in the U.S., you might have to go over and plug in your Russian reactor before you launch off your spacecraft. And if the Americans don't do it, the Chinese will be glad to. So
yeah.
I think there will be sources for nuclear reactors down the road, and more of these missions where people work. You might get your launch from SpaceX. You get your you've installed a Chinese-based capsule on the top. You've got a Russian reactor. You know,
yeah, that's not going to happen in the United States, but other nations may be able to
happen
pull it off.
it'll happen in Canada then. We'd be glad to launch such a Frankenstein spacecraft. Okay, cool. So Josh Andrews notes that Fermilab has done neutrino communication. So
I'm not sure how communication. They've sent signals that repulsed, and people figured that out.
We are sending neutrinos. Are you receiving this? Yes. But you can imagine. I mean, the great thing about a neutrino is you could communicate through the Earth, right through the Earth. So. You know, I could point my neutrino emitter at you on the other side of the Earth, fire a beam, completely secure. No one's going to be able to interrupt that communication. But you do need to have a great big vat of water when you capture neutrinos and detect the slight, you know, particle decay that happens when they collide. So it's not the cheapest form of communication. No. Better to use a wire.
Yeah.
Well, I'm all out of questions on the Google+. Do you see any questions anywhere else?
No, I see people happily watching us. Oh, wait, here we go. Minowit is saying, why doesn't the solar wind affect dust on our moon, i.e. erasing the footprints of the astronauts? Well, the truth is, it is very, very slowly doing that. So it's there's this constant bombardment of micrometeorites, of irradiation from the solar wind, and all of this over time is eroding the footprints, but it's thousands of years in order to do enough damage to actually erase them. But there are folks who are out there and who've calculated how long it's going to take before they're fully erased via strictly a micrometeorite process versus something coming along doing flump. And the much greater concern, and this is something that NASA guidelines are currently starting to address, is you can imagine hovercraft coming along, diving over, using rockets to hover over the surface, and those rockets blast out an entire Apollo site and ruin all of the footprints. And so some of the lunar heritage projects are working to define how do you protect the moon from having things like that wipe out these heritage sites.
Yeah, I got nothing else to say.
Okay.
But no, that's again, we just did an article on that as well about the there's a zone around the landing sites that NASA said don't hop, don't fly, don't jump, don't crawl, don't walk.
And they had to do this now because the Google Lunar X Prize people are getting ready to go there and rove their little rovers.
Yeah, or hop, or
hop their
wiggle, or however they plan to move around the surface of the moon.
I want a dancing robot to win. I mean, can you imagine? So the Google Lunar X Prize is you have to go to the moon, you have to go 500 meters, you have to send back a video. So imagine that you have
moonwalk.
Yeah, so you can have a robot do the moonwalk 500 meters. It's not effective, but it's fun. Great publicity for the company that does it. Send back a video of the dancing happy little robot. And yeah, sorry, my happy little fantasy world has leaked.
Yeah, that'd be good. Well, that'll be our entry, a dancing robot. All right, well, why don't we wrap this up, Pamela? And so if anyone's interested, we will be doing the weekly Space Hangout tomorrow, 10 a.m. Pacific, 1 Eastern. Now, are you doing the Science Hangout tonight?
I think so. We're a little bit discombobulated today because I had airplane issues yesterday. So there may or may not be a weekly science hour in 2 hours.
Okay, and we'll be doing our live virtual star party on Sunday night. And then almost immediately after that, on June 5th, we'll be doing our live coverage of the transit of Venus right here on Google+.
So stay tuned, everyone.
All right. Thanks, Pamela. Thanks, everyone, for watching, and we'll see you next time.
Bye-bye.